Hello everyone, I'm Sumit Vishwakarma, Product Manager from Siemens EDA, along with my co-presenter Eric Hong, Senior Director of Engineering from Mixel. We will be talking about analog and mixed signal verification methodology adopted by Mixel for high-speed, low-power MIPI PHYs using TSMC 5nm FinFET process. We will start with the updates in the MIPI world, then go over Mixel overview, and finally talk about mixed signal verification challenges and how to address them with Siemens EDA tools. MIPI Alliance started in 2003 to establish an efficient interface specification for mobile industry, such as interface for cameras, displays, 4G, LTE, microphone, etc. With its popularity and success, it has been now adopted in a wider application space such as AR/VR, automotive, and IoT. So why is MIPI widely adopted today over other standards? It's because of some key differentiations. The most important ones are the low power consumption, which enables power efficient data transmission between components, and low electromagnetic interference. Reduced form factor minimizes pin counts, and high bandwidth supports allow for high-speed, ultra-low latency interfaces. The other advantages are 5G readiness, security, software and debug capabilities.
Thanks, Sumit. I'll provide a brief overview of Mixel. A quick introduction to Mixel. We are industry leader in interface mixed signal IP. The company has been around for over 20 years and with a focus on MIPI specification since 2006. Mixel specialized in MIPI PHY and was the first IP provider to demonstrate silicon-proven D-PHY, C-PHY, and M-PHY. We also have multi-standard SerDes like C-D-PHY combo and LVDS D-PHY combo. We provide a completely integrated solution including the PHY, controller, and platform with many silicon proven in IP in 11 different process nodes and 8 different foundries. Here are a selective list of Mixel MIPI PHY customers. There are many others that can be disclosed at this time. I will now talk about MIPI in automotive application. Automotive industry is going through a major transformation. There's a growing adoption and embrace of electrical vehicle, increasing vehicle automation, critical need for tighter security, fuel efficiency standards are getting tougher and stricter. Cars are becoming like smartphone with features like high resolution dashboard display connected to backup rear camera, infotainment display with GPS navigation, multi-wireless Bluetooth, Wi-Fi, and 4G and 5G cellular network, advanced driver assistance system, voice recognition, voice command, and automotive driving system. These features are rapidly adopted by automotive manufacturers, and we see growing adoption of MIPI in this application. Mixel provides a combo C-D-PHY IP with smaller area and high performance, which can be configured as D-PHY or C-PHY. This combo IP supports both camera serial interface and display serial interface. The D-PHY mode supports the latest version 2.5 standard, and it has up to 4.5 gigasymbol per second per lane with discrete calibration, and has up to 4 lanes with 18 gigabit per second aggregate bandwidth. Our C-PHY modes support the latest version 2.0 standard, and it has 4.5 gigasymbol per second symbol rate per lane, and it has up to 3 trio with 13.5 gigasymbol per second or 30.78 gigabit per second aggregate bandwidth. On the right, you see multiple generation of our C-D-PHY combo test chip we use to silicon prove our IP. Our latest C-D-PHY test chip is in TSMC FinFET Process. With our C-D-PHY combo solution, area overhead is minimal since serial pins are shared between C-PHY and D-PHY mode. All D-PHY blocks are reused for C-PHY. Our C-PHY support the latest new features like fast bus turnaround ARP mode, which help reduce number of wire, power saving modes like half swing high-speed mode for D-PHY, low voltage high-speed mode for C-PHY. The right block diagram shows the block diagram of our C-PHY combo. The blocks in dark oranges are common block for D-PHY and C-PHY. The block in light orange are only used for C-PHY mode. Now let us review design and verification challenges. Higher display and sensor resolution and faster frame has continued to lead to higher PHY data rate requirement. Higher data rate requirement entails additional design complexity like advanced equalization, calibration, and link training. Due to limited thermal design power budget, it is extremely important to continue to improve power efficiency of PHY while extending PHY bandwidth. Minimizing pin count and die area is also crucial for reducing the cost of SoC and reducing PCB manufacturing cost. There are many custom IP verification challenges to ensure first-time silicon success. With traditional SPICE simulator, there is a capacity limit on number of components you can simulate with. With data rate increasing, link timing budget shrinking rapidly. So this necessitates tighter accuracy for simulator as well as SPICE model. Moving to advanced technology, we see SPICE model becoming more and more complex with tons of layout dependent effect. We see device noise increasingly impacting circuit performance with higher data rate. And reduction of simulation time with fast SPICE solution is very critical and essential for reducing time to market. Here are some of the key electrical specs for our MIPI C-PHY TX and RX combo. I will now turn over to Sumit.
Thanks, Eric. As Eric mentioned, shrinking process geometries imposes many growing challenges, such as increasing fabrication cost, increasing parasitics, increasing variability, more complex FinFET devices, and increasing interconnect resistances, which can impact signal delays, signal noise, and IR drop. Moreover, with smaller geometries, long-term system reliability has been a dominant requirement for safety-critical applications such as automotive. There has always been challenges to match what is simulated versus what is fabricated. And now, with lower nodes, this gap keeps increasing. This can be attributed to many factors such as model accuracy, simulator noise, layout and thermal effects, etc. on the simulation side. And on the measurement side, uncertainties due to test equipments, methods, and resolution, etc. contribute to this gap. Let's talk about Siemens EDA AnalogSpice Simulator next. One of the challenges that analog and mixed signal engineers face is to match the simulation accuracy with silicon. This can be achieved by tweaking the simulator accuracy to the highest level, but that drastically impacts the simulation runtime, making it impractical to achieve tape-out deadlines. AFS platform delivers nanometer SPICE accuracy with 5x faster performance than traditional SPICE and 2x faster than parallel SPICE simulators. AFS has been used by more than 175 customers worldwide, and it's foundry certified down to 3 nanometer. At shrinking nodes, we cannot just rely on schematic-based simulation results. Schematic is not the design, layout is. Post-layout simulation captures the correct timing and power performance of the design and must be part of the simulation sign-off flow. Though post-layout simulation is a must, it has become a bottleneck due to increased number of parasitics, interconnect resistances, and model complexities. Post-layout simulation at single-digit nodes demands higher capacity and performance from the SPICE simulator. To address the post-layout bottleneck, we have now introduced AFS Extreme technology. It applies a new adaptive matrix solver and new RC reduction algorithm, allowing designers to further increase simulation performance while meeting the user-defined accuracy. All of this is available within the existing AFS platform at no additional cost for new and existing customers. As a testament to the performance improvement of the AFS Extreme technology, here are several examples of the speed up that you can expect when utilizing this technology for your post-layout verification needs. From a successive approximation register ADC to a transceiver design to an SRAM timing simulation, these examples show a range of performance improvements up to as much as 15 times faster. Initial customer benchmarks show a 3x performance acceleration compared to commercially available solution at similar accuracy settings.
Thanks, Sumit. We now move on to presenting silicon result from our 5nm test chip and simulation result from our 5nm IP. We achieved first silicon success on our 5nm test chip with full functionality verified. The waveform on the left shows the very stressed eye used for C-PHY RX zero tolerance test at 3.5 gigasymbol per second. The one on the right shows a very stressed eye used for D-PHY RX zero tolerance test at 4.5 gigasymbol per second. A very robust RX operation from both C-PHY and D-PHY mode across PBT has been confirmed from our silicon characterization. We have seen good correlation between measurement and AFS SIMs. Next, RX eye diagram you see here shows that our CTLD design opening up internal eye very nicely from completely closed eye at RX input. We estimated the internal passing window through sweeping the skew between data and sampling clock and check the pass and fail status from our data pattern checker. We have seen good correlation in horizontal eye opening between silicon and AFS SIMs. In this slide, we summarize simulation time comparison between AFS and other simulators for different types of SIM, including PLL closed loop SIM, high-speed mode, and power down mode. And we saw simulation time speed up of 2.3 to 4x for AFS over other simulators. Here you see MIPI D-PHY TX eye diagram at 5 gigabit per second speed from AFS SIMs based on top-level simulation with full package and PCB model from our N5 IP. In order to capture the worst TXI, simulation with very long sequence of data bit needs to be done. So reducing simulation time is very critical for this type of SIM. And the simulation accuracy is very critical for predicting silicon performance accurately due to ever increasing data rate and ever shrinking timing budget of serial link. The next slide shows the full closed loop PLL simulation from AFS SIM. Both PLL lock time and minimal peaking result matches very well with what we expected based on PLL loop design. Next, let us review Symphony mixed signal verification flow and result. I will now talk about challenges for MIPI C-PHY mixed signal verification. We need to validate the interface between hard macro in analog and full custom digital design and control interface logic in RTL. Due to the extensive 5 functional and deactive features, we needed a high-performance verification solution with reduced simulation time that cover all different 5 modes. High-performance mixed signal simulation is also critical for verification closure. Digital simulation alone does not provide enough verification coverage due to the limitation with digital modeling of an analog block. Achieving both high performance and accuracy is essential. This slide showed a Mixel verification methodology for N5. All of the block level design verification, PVT characterization, and top level analog verification were performed by AnalogSpice and AFS-XT. The full 5 top-level functionality with custom and RTL block were verified with Symphony mixed signal platform. I'll now turn over to Sumit.
Thanks, Eric. Symphony is industry's fastest and most configurable mixed signal solution to accurately verify mixed signal design. Symphony has 4 differentiating characteristics. It uses AFS-XT solver to provide the fastest speed with accuracy and scalability. It offers the highest flexibility, and it works with any third-party digital solver and provides the maximum reuse of your verification infrastructure. It has the easiest use model with automatic boundary element insertion with minimal user intervention. It offers the advanced verification and debug capabilities such as high Z node detection as well as analog access function. With Symphony, we now have about 80 plus customers using Symphony in their product tapeouts. Symphony has been proven over a vast spectrum of design applications with performance ranging from 2 to 8x over legacy mixed signal solutions. Here on this table you can see different applications ranging from SerDes to PLLs to ADCs and PHYs and CMOS image sensors. Now I will pass on to Eric to talk about Mixel Symphony mixed signal verification flow.
Thanks, Sumit. Here are the details about our mixed mode test bench and the block diagram of our test bench. The block on the left side is the control interface logic implemented in RTL. The right side shows the hot macro contain analog and full custom digital block. We have successfully verified the interface for all functional and bit mode using Symphony. Here's a Symphony run script and configuration file showing simulation option, design configuration, and multi-threading info. I'll now walk through Symphony verification result. The main goal of this simulation is to verify D-skew calibration operation for D-PHY mode to ensure the position of sampling clock is in the middle of data AI after calibration. The upper waveform show the analog signal on MIPI serial pins, and the lower waveform show digital control and status signal from digital portion of PHY. Let me conclude the presentation with summary. High-speed MIPI PHY IP has become a key performance I/O technology in next-generation devices supporting 5G, VR/AR, automotive, and IoT application. Mixel is an industry leader in MIPI interface PHY with demonstrated silicon-proven D-PHY, C-PHY, and M-PHY with TSMC. Although lower technology nodes have advantages of power and performance, huge post-layer parasitic can become simulation bottleneck. So meeting the block level and system level specification with high accuracy is paramount to achieve first-time silicon success. Mixel achieved first-time silicon success with its MIPI C-PHY combo IP in TSMC FinFET Process using Siemens EDA AnalogSpice and AFS Extreme Solution and Siemens EDA Symphony platform. With AFS, Mixel has achieved 2.3 to 4x simulation performance improvement over incumbent solution. With Symphony, Mixel is successfully able to run top-level mixed signal verification to verify all functional bit mode of IP. That concludes our presentation. Both Mixel and Siemens have virtual booths here at TSMC Foundry event. I would like to invite you to come and visit our virtual booth to see our customer demo. And we can also answer any question about our presentation. Thank you very much for listening to our talk, and thanks TSMC for giving us opportunity to present. I hope all of you, your family are staying safe and healthy.